delivery overall. Now, let's start with continuous integration. And again, as you may know, continuous integration, basically the idea is that you have this like some sort of like action that it will trigger whenever there is a new code or a push or a commit. It needs to build the package, build some sort of like a container and some sort of like executable, basically. It needs to do some unit tests and integration tests on those components. And then when all of this is done, your CI need to deliver this package or executable, whatever you have, to the CD, basically, continuous delivery. So CI is responsible to do all of this and give the task to the next part. Then when you go to continuous delivery on the other end, so continuous delivery is basically responsible for deploying the code and train model basically to a target environment. Ensures that it's compatible basically with that environment that you're targeting to basically sending it to. And it also checks the performance of the model before deployment. That performance could be some tests that you do over to see that overall, if this model is good in compared to the previous one. Or it could be performance as like a system performance, like how much it's RAM, CPU, and stuff like basically it utilizes. That becomes the last step before you basically send the model. Now, this becomes your CI/CD infrastructures. Basically, whatever you do, CI comes here, CI creates the packages, CD basically comes here, CD basically send the model, and then you do model serving basically. Now, when we talk about the unit testing in the CI, well, because we're talking about ML related basically unit testing. So there are two types of unit testing you can do. Unit testing over the data, unit testing over the model basically. So it's unit testing over the data, unit testing over the model. From the model perspective, an example could be, I'm passing this data, I expect the model to produce this number. That becomes the unit testing, for example. Now, when you go on unit testing over the input data, you can test for the feature engineering logic. That means if this data comes through and I did this process, it needs to basically generate this result for me. That becomes for the feature engineering. You could have some test values. You could have some formats that you want to, a schema, for example, you want to basically do a test over there. When it goes to the model again, and the model methods itself is one. So let's say you have this model and your model has different functionality. For example, you want to be sure that every functionality was saved with the model. Because imagine you have a model when you saved it, you have, for some reason, that .predict or whatever, like a predict batch, it's not part of this package. So when that model is deployed and the API wants to make call, it keeps getting error because that functionality doesn't exist. So you need to be sure you test all the methods that you want to be saved with the model. Okay. Test the model performance with metrics to be sure, test if your model has some bias to be sure that you can detect it. Be sure that you test your model for basically NaN or empty string values. Sometimes models basically tend to generate those. And again, there are more. This is just an example of unit testing that you can do for your model. Okay, but it's important to just keep that in mind. You just don't pass it. Now, when it comes to unit testing consideration, so you can. We did have mocking in our lab, correct? So you have seen mocking before, basically, kind of like a way of testing your code, which without actually running the actual API calls and stuff like that. Basically, you use mocking. You want to be sure that when you use mocking, that you can cover all those edge cases or corners of your code. When it comes to the data coverage, again, also your mocking test should cover all sorts of data. That means the data that you are testing, it shouldn't be as the same size of large data, but it should be covering the same dimension of your training data. Okay, so it's just kind of like you covered the same features space to be sure that it can basically pass all those tests. And then you also need to do code coverage, that code coverage simple example is for the libraries, making sure that there's nothing missing. And then the last thing when it comes for your basically ML model pipeline is infrastructure validation as part of your CI/CD technically. Infrastructure validation is that to validate to see that I have a model, every test passed. If right now I give this to a customer, this customer is going to run it, for example, will this run? That's kind of like an infrastructure saving. Or if I just push this model from my GitHub and I push this package and I'm pushing this to basically GCP, will it break the infrastructure that I have already over there? Or will it basically run? So basically you do some infrastructure validation. There are some tools that you can use already for that, and TFX Infra Validator is just another library by TensorFlow. And what it does, it creates some sort of like a fake environment, like a sandbox, basically. Within that sandbox, basically it mimics that infrastructure, runs the model, and if it passes, and basically it can run the model and it passes certain tests, then it basically tells you that it's good. It's kind of like you build a sandbox environment to basically test out the model to like for that wherever you're targeting, basically on infrastructure that you're targeting. Now, so all of this is done. So you have this model, you have a proper basically CI/CD for this model, packaging it, sending it. Now the next thing is that, well, comes to the delivery part of the model. How are you going to deliver this model? Like, and how can you basically give it to the customer actually? How you decide who's going to use it, So the first thing as part of delivery is called like a progressive delivery, Basically, it's kind of like you have a model, this model is ready. Should you just give it to everyone right now to use it? Or should you basically kind of like have a schedule? Or should you only pass it to certain people and wait for their behaviors or feedbacks and then give it to the rest? So that's this next decision that comes for you is like how should we deliver this model to customers? Okay, so now there are some complex deployment scenarios. One of the things that you want to remember is that you can deploy basically multiple models. You can do some sort of like A/B testing for deployment. You can do something like a shadowing, like a canary test that we have talked about before. But there are different ways that you can deploy these models. Let's just start with the first one, this like the easiest one, blue-green deployment. And if you remember, the blue-green deployment is a scenario that you already have a model that you are serving it to a customer. And let's call this, I don't know, blue, code version 1 blue. So your model blue is the model that your customer right now using. You have a second model, the green one, and you want to start giving that to the customers. The blue-green deployment, the benefit it has this load balancer, which that's why it makes it pretty safe and easy approach, because the load balancer, all it does, it just switches the traffic to the next model. So technically, no one will notice a change because it's really quick. You're just switching the traffic to the next model. What you do, you technically keep the first version still available because you don't know what will happen. But if you all of a sudden notice that something is, you do monitoring, after deployment, you monitor for a period of time. If you notice something is going wrong, you switch back to the previous model. That's the blue-green deployment. So you have one version ready, you switch just the traffic, the load balancer switches the traffic to the next one. If something went wrong, it just switches back to the other one. Yes?
It's like canary testing, right?
We're going to talk about canary testing. You don't switch it, you gradually release it. Like what you do, for example, let's say this is a class and I want to take an exam and I give the first 5 students here an exam and I wait for the result. And then based on that, I decide if I should give the similar exam to other ones. So that's a canary testing. So you basically kind of like you test to see that if something is going to go wrong for a small fraction of your customer, if not gradually, you basically start releasing. Yes.
So it's like you have beta testers in Google Play who sign up for features that are yet to be released to the general public. Is that something like canary testing?
That could be. So you basically bring your, so there is a difference. I don't know how does Google does that. So it's possible Google does A/B testing. That means when you sign up for testing a product, they don't tell you what you actually get. You just test this. There's a same other group of people that they get different version. And they monitor the result, and based on that, they decide which one they need to basically test.
Some people's Instagram accounts are different.
So what's the difference between canary and A/B?
So we will go into get there. All right. Those are all great questions. So this is canary deployment. You just need to wait one slide. So traffic comes and you still have this load balancer, and your load balancer basically what it does, and you have these two versions of the models. So for certain percentage of you define what's that certain percentage of the model, it switches the traffic. So let's say you start really low, 5%, 10%. You pass 10% of your customers, users to new model. And you monitor what's going on for a certain amount of time. See that? And monitoring could be monitoring of the model, and it also could be monitoring the what is told out there. Like imagine you deploy a model, all of a sudden you do some analysis on LinkedIn, and you see that everyone talking bad about it. That hey, this new model is really bad and stuff like that. That could be a way of basically also detecting, right? So you monitor it, and if so far things are good in canary testing, then you release a second basically gradual release, like maybe another 10%, another 20%. You keep doing this until basically you get to the point that everyone has access to the model. The benefit of canary testing is that it's kind of like because you gradually release, you could basically monitor to see that if something went wrong and no one else maybe knows about your model. In the blue-green, everyone knows about the new model. And if something went wrong, everyone knows something went wrong. And here, only a certain percentage of the people have access to the new model. And if something went wrong, you just change their access to the previous model, basically. So this becomes the full canary deployment. And I think, let's go here. So the next one, we're going to go to A/B testing now. Live experimentation. And the first thing here is that always remember that model metrics is not the business metrics. The problem is that when you work in industry, the business metrics is more basically favored in overall. So you always need to find a proxy between your model metrics and whatever the business metrics is not. For example, in recommendation system, your model is trained on clicks. Based on that, you do recommendation, but business wants to maximize the profit. So it's really hard to map these two together. And so one thing here is that, like, for example, different products have different profit margins. So now let's think about this. So you have two models, and this comes back to what you were just asking. You have two models, model A, model B. And you're like, I don't know which one is better, because both of them are technically good, right? But a model could be really good in the lab, but in the production, it's not good, right? So the idea of A/B testing is that, or maybe the users, they don't like the model or something like that. The idea of basic A/B testing will be that you have some clients, some application, you have different models, so different groups of customers will get different access to different models. And you monitor basically performance, you do some basic hypothesis testing, and based on that, you decide which one is better, and you switch the rest of the users to the other version of the model. So that's the idea of basically A/B testing. It's kind of like but if you want to look at it in a general way, so A/B testing is kind of like you have this large data set, and you basically randomly assign people into different groups, and different groups get different, basically, let's say here, medication. And And you basically monitor the result that you have. Based on that, you decide that which one of those two medication is better, basically, to use for you. And it's really important as part of A/B testing to remember that that split of customers that you do it cannot be just random, because you need to be sure that the cohorts that you are basically doing testing is kind of like similar. Because it's really, let's say if you do a random testing across your user, one group of user comes from Massachusetts and one group of user, for example, comes, I don't know, from somewhere in Middle East. That comparison is not basically an apple to apple. Because you want to be sure that the cohorts that you're testing over, it's kind of like they're similar. Now, there's another way of for the live experimentation. It's called multi-arm bandit, MAB. This machine is called multi-arm bandit, right? I don't know have you ever played? I haven't, but apparently you go and you pull this down, and if you win, you win. Otherwise, you don't. So now the idea here is that this multi-arm bandit it's kind of like a live experimentation. You have series of models, not two. You have series of models, and you want to see that which one will win. So you basically have these models, and you basically distribute the traffic to different models, and you monitor. As you monitor, you have this ML model. You have additional ML models that look at the result and happiness of customers. And it start ranking the models, basically. It says that this model is better, top. It's kind of like a ranking. As you find the top models, you get rid of the bottom models, the models that are not good. You drop those and share the traffic back to the rest. And you keep doing this until you get to one model, which was always the top model, basically. So that becomes the multi-arm bandit. So when you have multiple models and you don't know which one, so share the traffic and have a model, some way of ranking the performance of each model. And the models that the performance is low, get rid of them and share the traffic to the rest of them and repeat this loop, basically. Is that clear? Yeah. All right. So then the last one is contextual bandit, basically. And that comes, the idea here is that, well, maybe we shouldn't just look at the performance of the model. Maybe we should also get some contextual information on top of the performance of the model in order to decide what's good or not. For example, is that user is in a different climate. Maybe that's why the result that they got is different, or maybe that's why they didn't use the model, because let's say you have a model for app for running, and then also the user, they don't use it. Why? Well, they in somewhere it's like in Massachusetts, and it has been snowing forever, right? So you need to basically have some contextual information in order to decide if a model is better than the other ones. All right, so what we do now, we just take a okay, so we're going to start with the MLMD or ML metadata lab. And I'm going to first there are a couple of libraries I'm going to basically import. The main one is ML metadata. Okay, that's the one that you want to import it. So we're going to get two things here. One is that metadata store and metadata store for protobuf. Okay, then I'm going to getting a TensorFlow and TensorFlow data validation. So again, you have this code. Then the next thing is that it basically just downloads the data. Okay, so that's downloads the data. Then this is what we're going to implement. This is what we want to do right now. Okay, so the thing about ML metadata or MLMD basically is that you need first, you always start with where I'm going to dump this metadata. Okay, so the four on the bottom, the options that you have for putting your metadata. You either decide, I want to do in memory, like for the rapid development on your machine, I'm just going to do in memory. You could do SQL later, basically write it on the disk. You can do MySQL, you can connect to a bucket or something, and there's all other options. But the other thing here is that in the previous class, we went over this. There are three basically main component that the MLMD overall, basically this general metadata generation has. It's going to be the artifact, it's going to be execution, and it's going to be context. Okay. So artifact again is just any input output generated by the model becomes the artifact. Then you have execution. Execution is that operation of running a certain pieces of code that receives the artifact and produces the artifact. That's basically like the execution that you do. Then you have context, and context is simply a group by between these two. You know, whenever you hear the term context, it's just going to be the group by between artifact and execution. Remember, execution, you just kind of like you hit enter, you run a code over your artifact. Right? So that, in order to map these two together, so later you can search and say that for this execution, give me all the artifacts. That's where the context is. That groups them together, like index them together, so you can search through that. Then there are three other relationships that we want to talk about. One of them is event. So event is the relationship between artifact and execution. We call it an event, right? Makes sense. Kind of like I ran the code is an event, basically. Then we have the artifact is an attribution for the context. The relationship that they have is called attribution. And the execution is an association, has an association relationship with the context. Okay, so overall there are three components, three relationships, and three data types. Artifact type, execution type, context type. Okay, so you basically have 9 terminology here, okay? Is that clear so far? So what we want to do, we want to basically bring data and get the schema for the data, statistics for the data, store those as in the metadata store, have a defined execution for it. Execution means that I get the data, I want to run it against this data and get the metadata and get the statistics. All right, that becomes the execution. And we want to also define this context and all this basically relationship among those. So that's the goal that we have here. So we're going to start here. So technically start from the bottom part. We need a storage first for everything that we generate, okay? So because I'm just going to do this in memory on my machine, so basically all you need to do, can you see the code or do you want me to make it larger? Good. So the first thing we do, we make a connection, metadata store protobuf 2, connection config. So you're basically first creating a configuration for that basically connection that you want to have. Then we see that that connection is going to be a fake database set in parent. Right? So that means that it's an in-memory database. It's a fake database in memory for rapid prototyping. And then you basically pick that connection config, and this is something that we loaded above, like imported metadata store, and you add that connection config to it. So now you have a storage, okay, it's called this one, this is your storage. And this storage has this configuration that runs in memory, and it basically acts as a storage, you know, that you can basically dump the data and query against the data. Does that make sense? So if you're basically doing something else, so this will change. So for example, database here, MySQL, Postgres, SQLite. So it has basically different options for you to do that. But we just wanted to be in fake database set in parent. So that's what we use. So the next thing we want to do is that we want to define the artifacts, the first types of basically data that we need. It's going to be the artifacts. Because again, artifacts are the like input output basically. So yeah. So what do we need for artifacts? So first one is going to be, remember, for data validation, what do you need? You from your training data, you get a schema, you get a statistic. From that, you get the schema, And then for any new data, you compare it against those two. So we are starting with then a statistic, artifact. So we're going to create an artifact type, basically data, or basically type for the statistic. And the way that basically you do is, we will see the functionality is pretty straightforward. Metadata store protobuf2.artifact type. Okay, so you're creating a variable of artifact type. Then you basically, whatever field that you think you need to give to it, you basically add those. It's just you are creating these artifacts. So first, you give it a name, artifact type.name, then artifact type dot properties. You add additional whatever properties that you want to add. It's kind of like this technically a protobuf. We will see later, but so basically you say that I'm going to give it the artifact type has a name. It also has so name is fixed here. You see, so we give it statistics. Then you create these fields like properties, like a name, a split version, and those are not fixed because you can reuse this artifact type later. So what you do, you just say that this is going to be a string. Whatever you will pass later to it, this is going to be a string basically. Okay, so you define the artifact name fixed, but the properties are just, you put a placeholder basically. These are going to be a string basically. Then what you want to do is after you define all those properties that you need, you want to add that artifact type into the storage that you have, that metadata storage. Okay, so if here. So if we do something like this, so let's say you have this metadata storage that's like in memory, and you have this artifact type, for statistics. You're going to put this here. Okay. And in order to do that, you basically store is the name of that storage, that variable that you find a store dot. And see that you will see the functions that are pretty straightforward. Dot put artifact type. It's like a pretty straightforward the way that they create those. And you put that artifact types here. When you do that, in reverse, this will give you an ID. It's like index it for you. It tells you that how you can basically retrieve that later. So it tells you there's an ID related to this basically a statistics artifact type. So then we're going to basically do similar thing. This time we're going to create an artifact for the actual data. So we say data artifact type and repeat the same thing. Is going to be an artifact type. You call it the data set and you decide what properties you need again for that data set. And you pick that data set and you put it in the artifact, and that gives you a data ID basically. So you have data artifact. You pass it here, this gives you an ID. Okay. And the next thing is that it's going to be a schema. So you have a statistic, data, and the next comes a schema. Again, same thing. You just give it a different naming. And here you have two fields, name and version. You don't have a split because schema comes from the training schema. You don't need the validation schema or inference schema. So you do the same thing, add the schema to the here and get basically the ID for it. So that becomes the third one. So we have a schema artifact goes here and you get an ID. Okay. So, and this is, so if you look at the artifact type, this is this artifact type basically. It's going to be, as you can see, it's kind of like a protobuf. This kind of look like a nested JSON, but it's not a nested JSON. Then it's just a printout, and at the end, this is the ID that you can basically access those elements, okay? So that's for the three artifacts that we define, and these are just, we define the artifact types, okay? It's kind of like a placeholder, technically. The next thing is that we're going to go over the executions. So we want to also define some execution. What do we want to do? What our pipeline wants to do? Data comes, we ran the training data comes in, we did the schema, statistics, and data itself. Now, every time new data comes through, I want to do a test, like an execution. I want to run, compare this new data against my trained data, statistic and schema, and validate it if it's like an anomaly or not, right? So you need basically an execution for that data validation, okay? So, and again, functionalities are pretty straightforward. Metadata store dot execution type, that's, you create the empty placeholder, then dot name, give it a name. And you also, so because this is an execution, it's like something that's running, right? So execution need to have something called a state. A state means running, finished, idle, and stuff like that. This could be because it's a code technically, right? So you define a state and you say that's going to be also a string. Then you want to put that in the store. So here we have the data validation execution. Execution. And we add this here and it gives us also an ID for that. But in order to store it, this time you say store dot put execution type. So this previously was put artifact type. It's like a put execution type. And you run that, so basically you get this, there's a data validation and there's a key. It's called a state, there's a value, it's supposed to be a string, for example. Now, so you have 4 things, but what we have so far, they're a placeholder. We just build basically like a metadata store and says that you're going to store these types of data. And we define the properties for these types of data. Now we want to define the actual data unit, basically. So we basically going to start with data itself, you know, so this one, data. So what we want to do here is that you want to build an actual, so here we build artifact type, right? What we want to build an actual artifact for the data. So you start with metadata store, basically dot artifact. Previously was dot artifact type, just for data type. Here you're actually building the data. And because now this is an artifact, you basically give the address to where is this data. So data artifact dot URI, and this is the address to the training data. Okay, so you match basically your artifact for data to actual data on your machine. So let's say we have data artifact. Okay, so this data artifact adds to the data itself. Okay, actual data that you have. Then you want to connect that data artifact to this one. Okay. And the way you do, all you need is to match this ID to that one. So basically you say data artifact type ID, because you just build an artifact. You don't know what's the type of this artifact. Type ID, and you pass this ID to it. So this ID technically goes here. Because when you do something like this, now all the properties that you define here for this data type, artifact type, will go there. Okay? So then we know out of the properties there was a name, a split, and version. So you assign the values to those. What's the name of the data set? Split, this is a trained data set, version 1. Okay? And again, those properties are the fields that you define based on what you think is more important for your task. So the next thing here is that now you built an artifact, you connect it to data type, basically artifact type. Now you actually need to store the artifact also into the storage, right? So you basically say store. So previously was put artifact type or put execution type. Now it's just put artifacts. The function. The function as basically what it requires, it gets as an input a list. So if you have just one artifact, you still need to pass it as a list. And when you put it back, basically when you put this here, because you pass as a list, when it gives you ID, it technically gives you a list of IDs. And that's why here I say that give me index 0 because it just was one element. So I want the first element of that list, which is the ID to access the data artifact. So, is that clear so far? All right, so now what do we have? We have the data artifact and we have, let's see, we defined data artifact, we define execution. Okay, so now the next thing we do, so we have one execution. Okay, now we're going to basically define actual, so that's execution type, basically. We're going to define an execution basically itself, like as an element. So metadata store dot execution. Same thing is going to happen. So basically you create an execution. And this execution, the first thing is that you connect it to this ID for the execution type. When you connect it to the execution type for the ID, it has some properties that you can use. One of them was state. So this time you change the state to running because this is going to be, as soon as you store it, it's like a running basically operation. So you change the state of that execution to running and add the execution to the storage. The store.put execution as a list and get because it's only one, get the index for that. So I then add this here and this gives me an ID basically. Okay, so if you do that, basically this is what you're going to get. Now remember that we have execution and then we also have the artifact, but they are not connected to each other. And the connection between execution and artifact was called an event, the relationship between those. So what we want to do is that now we want to create an event for that between the data and that execution. So you basically metadata store dot event, you're creating an event. And if we go up here, what you will see here is that for all of this, what do we need for an event? Event has two sides, execution, artifacts. When we go to attribution, what do we need for attribution? Artifact, context. When you go here for association, we have execution, context. So that means anytime you create any of these three, event, association, attribution, you need to connect it to two different IDs, depending on what you are connecting to. So if we go back, here, okay. So now if we go here, we create basically an event, and that event basically is the input event dot artifact ID, and we pass the data artifact ID. So we are going to create an event. This event will get the ID from here and ID from here. Okay, so it has two. This event will get an ID from execution and ID from data artifacts. Then we define a type for it. So here basically just the type of thing that when you work with the library, you see all the data type basically or types. Here we say that this input event type is called input, declared input. It has declared input, declared output, and series of basically type that you can declare. Because this is just an input data that we are passing, so we call this declared input, okay? And then all you need to do is that store, and again, you see the terminology is straightforward, put events as a list, you pass the event. But this time we don't technically, we're not getting the ID back because it's just an event technically. So, and that's what you're getting. So input event is connecting these two artifacts, one artifact ID, one side execution, and the type is declared basically input. So now for the next part, I want to add the schema and a statistic also and create basically events for those. Instead of manually creating the schema, I'm just doing basically small like a workaround. I'm using the TFDV, give the data to tell me, give me the schema, I get the schema, then I add the schema here. Instead of we manually try to come up with the schema, we just use the other library to give us the schema. So, so we have this training data. We pass it to TFDV, generate the statistics from this, and you get TFDV infer statistics from the infer schema from the statistics, and basically we write it to a file. Basically, we get the schema and we write it to a file. Okay, so it's done. That's the schema basically is generated for us. For every data point, basically it has the information. Now what we want to do is that we want to, so similar here, we did an artifact for the data. Here we have this schema artifact type. We want to create an artifact for it also. So we want to create an actual artifact for a schema, connected to this ID, connected to that schema file that I just generated, and then add it here, and this will give us another ID back. That's basically the same process. So we start by creating an artifact, and the address to that artifact, remember similar to the data, we passed the address to the data, we pass the address to that schema file that we just wrote to the hard drive. We connect it to the ID, we give it a version, we give it a name, we put it into a data, basically a storage, and that gives us an ID back. Okay, so now we have, for the schema also, we have an actual basically artifact and stored in the metadata store, and then we have also the ID for it. The next thing is that similar story. Now we need to create an event for the schema basically. Okay, so it's like a, so we created another event. We connect that event to the schema artifact ID. We connect it to execution ID basically. Okay, we can connect it to execution ID, and we just store it in the into the database. So by doing this part, basically, you have an actual artifact, you have a piece of code that is supposed to be running. You connect these two together, just that this is running and this is connect. This is the artifact that is running over. You basically create this connection. Oh, sorry, here we call this declared output, because it's like the data was the input, this is the output of that process basically. So then okay, so now technically what we did, we have this loop, kind of, sorry, this is messy here. So we have data artifact type and data artifact, and we connected that to this event, to this execution, sorry, okay? And when we connected the data artifact to this execution via that event, what did we say? We say data artifact declared input event, remember? So I'm going to just try to draw this further now. So if you think about it, so we have data artifact. And then we have this execution. And then we have this event. Correct? So we connected this here and this here. Basically, we created event. We connected event to ID from here, ID from here. But also, we basically say that this event is declared input. Okay. What does that mean? That means this event, which is execution of a code over this artifact, is an input process, basically. Okay. The next thing we did here, we basically created another artifact, and that was called a schema. Right? Then we brought that schema and we created another event. Okay. This event is connecting the same execution to this schema artifact. Okay. So this execution is being used two places. Then we say this declared output. What does this basically tell here is that for this execution, basically an event, one event is input, getting the input. One event is to generate the output. So this schema generation becomes the output that comes from, so whatever code here is, that code is supposed to get this, basically generate this schema and becomes the output. Does that make sense? Yes? Question on that? All right, so. Okay, so cleared. Oh, we already did this. I already ran this. So now, what the next thing now we want to do here is that this execution, remember when we started, we put the state to running, correct? When we first created this and connected these two, we set the state to running. Now, because this is done, you need to change the state to, for example, finished. It's just a manual process. So basically for that execution, you change the state to complete. So that is done. Basically, that's the way for us declaring this is what the process is done. Now, so now we have technically everything we need. So the next process comes around the context, how we can group all of this together. So we start kind of like a similar way. So we first create a context type, basically. So you're going to do a context type, and we had this metadata store, MS. You put this context type here, and this gives you back an ID technically. So you create a context type, give it a name, give it the properties, for example, and add this to the storage, and that gives you an ID. Okay. Now, after we have the type, then we are going to create an actual context. So basically, we do this like a context, and that's basically a type itself. So you connect that context to this ID. So you get the ID from here to here. You connect these two together. Because we connected now, it has the same properties, name and the properties. And after that, you just put this into the metadata store, and this will return back you an ID for that context. Okay. So okay. Now what we want to do, we want to create the relationship between the other ones. So we already declared the event, which is the relationship between those. Now, what we want to do, we have basic attribution and we have association. So if you remember, the attribution basically is the relationship between artifact and the context. Association is the relationship between the execution and the context. Okay, so you basically start and say that, well, I'm going to create an attribution. Because it's attribution, by default, we know it needs two things, an artifact and a context. Okay, so what is the artifact ID that you want to connect to? Here we say we want to add this schema. So you basically bring the schema down and this context. Basically, you connect these two together, and that is becomes attribution. So you just create an attribution and you connect two IDs to it, basically. And those IDs should be some context and some artifacts. Then you go to association. Basically, you do the same thing, but this time you do association for the execution, basically. Okay, so that becomes the association, and you connect the two IDs that you want to it. And the next thing what you want to do is that you want to put them all together. So the way that the library has code for that, put attribution and association. You just pass them individually as a list, basically. But the function is one, basically. So you basically add those basically to the metadata store. And the next thing is that now, so you imagine what you're basically seeing here is that, so when you build the pipelines and you're basically using your own code, you're not using pre-built libraries and stuff like that. So you need to basically build this this relationship, to a great extent. And let's say as you go through your code and you basically have all of these components, and now you want to retrieve basically information. That means you want to go back to this metadata store and do search and get something back. So if you call to storage, get artifact type, it gives you list of all the artifact types that you have basically added there. Okay. Then, for example, you say storage dot get artifact by type, and you say that it should be a schema, and give me the first one. And that's just a way, for example, for you to retrieve. You can say storage get event by artifact ID. So let's say you have the artifact IDs and you want to just query against the artifact IDs, you can basically do that. You can do get event by execution ID, just that's another way. And so here also you can store get artifact by ID. That's whatever is the artifact input dot artifact ID you can use. So there are different ways that you can query against this basically overall. And that basically, that's kind of like a wrap it up. Just that I know there are too many pieces here, but if you think about from perspective of if you want to build some pipeline that has all the components, has all the relationship, you can basically monitor, you can query against, and you're not using any out of the box basically libraries for certain reasons, then you need to basically remember this. Basically, there are three types, three elements and three relationships. Overall, 9 things. And this ML metadata library is open source. Is the functionalities are pretty straightforward the way that they wrote the function names. And you just need to remember this 9 basic things that you learned, But one other thing that is really important is to figure out when something becomes input, when something becomes output, how you connect this together. You also need to remember when you have an execution, when the execution starts, change the state maybe to running. When it's done, change the state to basically terminated or finished, and things like that, basically. Any question? No? All right. So So there's a second lab for yourself to try that one. So I leave that for you. That one is a bit more advanced, just what if you want to have a schema that changes? You know, how you basically could manage that. What we want to do now, so we're going to do one lab on TFT and then one lab on TFX. So the idea for the TFT is TensorFlow transform. It's basically how to create some sort of like a data transformation pipeline that it can manage and it can scale with a large amount of data. It's kind of like optimized basically version. I personally believe that TensorFlow is like pretty optimized for this type of thing. So there are a couple of imports that we do, but the important one is this one from tfx.public import tfx.io. IO becomes input output basically. So what happens here is that TFX basically, because if you remember, as I said before, the TFX, what it does, it gets other TensorFlow libraries and unify them together. So you can basically, instead of installing every individual TensorFlow libraries, if you install TFX, it has all of those basically, okay? But the challenge that this basically package has is TFT, TFDV, TFMA, all of those libraries, they have a different style for model input output as an artifact. And instead of every time trying to map, what they have done using this TFX.io, TensorFlow basically input output, they convert the input output to a unified version. So every library is basically they can use it. So that's the idea. So this TFX.io that's basically what it does. Now, we import the Apache Beam to use here. And then also as part of the TensorFlow transform, because technically it runs on Apache Beam, you can also do TensorFlow transform import Beam as TFT Beam. That's a version of the Apache Beam that runs within the basically TensorFlow transform. And then we import also dataset metadata and schema utils. So there are a couple of imports I would just do, they're necessary for as we go through this. There's a data that we get, so data basically looks like this. So it's kind of like, I think it's like a data for wind. There's a date time over there, and there's not like some wind degree, maximum wind velocity, and things like that. Okay, it's like a time series data. So there's some code for data transformation, or sorry, data EDA. But here, basically, what we do, we define, we break down our features. So one feature is timestamp, and the rest are numerical features, just for the processing. Then this is just for visualization. So if you run it, basically, you will see that these two time series, they have kind of like an outliers basically over there. And you can basically fix that outlier. So we fix that outliers. Oh, I didn't visualize the, I didn't load that. But there's some correlation also, which shows the correlation. This is just EDA. That's why I'm just passing through this part. It doesn't matter. So here, and then after the correlation analysis, you decided that you want to drop these features. You save the name of those features as features to remove. And so now we come to this part basically, and the two types of basically features, timestamp feature and numeric basically features. You combine those, and those are like an ordered features. And the first one becomes the basic index. Your data set has an index of time. So the first column that you pick here becomes the time index, basically. And basically, here you have this function, clean function. So this function, what it does, for every data, every line, every row, basically, that you pass to it, It's split the data because it's kind of like it comes as a byte and decode it because again, because it's byte, you need to decode it. Then it checks the date time, gets the timestamp, and it basically convert the timestamp to byte and then UTF. And all it does, if the timestamp is wrong, it basically changes it to 0, and then so this is for the cleaning basically. So this is the same thing that you saw up here for these outliers. That function, all it does, if there's an outlier like that, it just cleans it for you. So this part is just, I go through this fast. Now, so then there's the next part is like again, because it's like a time series data and wind, some data around wind. What we are trying to do in this pre-processing function to get rid of some of the features that they were not important. And then you have this wind velocity that you want to convert it to basically two new columns, W like a wind X and wind Y. And you want to use that using like a cosine and sine functions. So basically this is what basically we use for that. Then we get the day, year, timestamp, and then we create a bunch of new function. And all of this function, as you can see, we are kind of using TensorFlow, you know. So we are not using any other libraries. We're using TensorFlow. It's important to keep in mind if you're not a TensorFlow user, if you use libraries or functionality out of TensorFlow libraries, like a scikit-learn or something like that, then your code is not a TensorFlow code, and you can't run it directly. You need to declare that code, decorate that code as a tf.function or something like that. Otherwise, you will get error. So, so here, basically what it does then for these features, it scale them. TensorFlow transform scale to 0 to 1. So like numerical features, we just scale them to 0 and 1. So it's just a pre-processing function. Now, so then this part, just the train test split, it just split the data based on the timestamp. Like, we don't need that. And then there's this function, partition function. So basically what we are doing right now, we are creating all these functions that we want to use later. And this partition function will be responsible for train test split. And what it will do, it based on the timestamp. If the timestamp is after this train boundary, which that's defined here, then it will return 1. That means the training data. Otherwise, return 0. But this partition function will be used as part of the Apache Beam. And Apache Beam, when you pass like a partition function, it technically needs to have an input and this parameter called number of partitions. We are not actually using it here, but when you create a function like this that you want to pass to Apache, you need to have that parameter basically. Okay, so this is not being used here, but you need it. So now the next thing here is that we want to create a schema for this data. And here basically what we do, we first create we have our data, we just create a placeholder for a schema. And what we do basically, or not a schema, but maybe call it a spec. We basically create this dictionary for, and we have two types of features. We have the feature timestamp features, numerical features. For each of these features, we create a tuple as a name, the name of the feature. TF input IO fixed length feature is like a data type basically you create. Empty value, and it's going to be float 32. Empty value, float 32. So you basically loop over all the feature names that you have, and you create this raw data spec, and it looks like this basically. Okay. So, and then then we want to create basically a schema for that. So we can pick the same data spec that we created, raw one that we created. We can basically pass it to this basically function data set metadata. And that will give us a raw schema. A schema that's not filled, it's just built from the spec. So data set metadata, schema utils, a schema from feature spec, you pass that, and it gives you this raw schema. Why raw? Because it hasn't been passed like a ran over the data. So it just has fields based on the data, the column names and the data types, but it doesn't have the actual information. Okay, so now we have raw data feature spec, raw data schema. Okay, now the next thing is that, okay, we're going to start focusing on the building the TensorFlow transform pipeline. So yeah, we define a couple of directories. We have this function read and transform data that reads data from working directory, wherever the data is loaded. And then similar to the lab that we had for the Apache Beam, so you start with beam.pipeline as pipeline, and then now we want to do the same thing that we saw before. We want to create a context for basically connecting these pieces together. So with TensorFlow transform beam context, and here basically what we say for the context is that we basically have this temporal directory for this context. So it's kind of like a place that we can basically have temporally the values stored. That's going to be working directory, transform temp directory, like a join those two together. So the next step here is that, so first thing you need to read the data from the hard drive. So raw data, you use the pipeline, read training data, and we saw this before, beam dot input output, read from text, wherever is the text. You put a coder for it because the data is a byte data. So you need to do coder beam.coders byte coder. And because the data has a first row, which is the header, you basically can say skip the header lines, basically. Okay. So that basically reads the data. And you remember we talked about kind of like a chain rule. So then you go to the next line over the same data. I want to clean the data. Beam.map, you map it basically, and it clean, you had this clean function, basically it cleans the data for you. And that becomes the raw data, okay? So if you have a raw data, the next thing is that split the data into train and test, for example. So raw train data, raw test data comes from this operation. So what do? We basically pass the raw data to this basically part. So you have the raw data passed, this we call it train test split. And remember, we had this function that I just saw, a partition function, and I said it has a parameter that we didn't use, but Apache Beam needs it. So that's this part, beam.partition, and you pass that partition function, and you say basically, I'm partitioning in two pieces. And Apache Beam, what it does basically, when it uses this function, that's the two for the number of partitions. Okay, so it's kind of like it says, oh, I'm creating two partitions basically. So this up to this point now, we got the raw train data and we got the raw test data. So now, so we kind of now what we have a train data. We want to basically create that schema. Remember, we had that raw schema. We need to basically create the actual schema for that. So here there's basically from TensorFlow TFX.io. Basically, I say that that's for the mapping the correct format data types. Beam record CSV. Basically, we say that we're going to read physical format is a text file. We have a list of the columns, and we have a raw schema for it. Okay, so that basically creates some sort of like a mapping between the data and that raw schema that you have. Then the next line, basically what you see here, we bring that training data that we have, and we kind of basically decode it, you know. So because remember the data is kind of like encoded. So you decode it using this, basically that's what we got. You decoded beam.source. Now you get the actual raw training data. Now you have the raw training data. Let's go here. we want to get the metadata from that raw training data. So you basically say CSV, TFS, IO, tensor adapter config, and that gives you the metadata around the basically the data. Then this part, basically what you do, you create a couple of raw data and metadata together. So here you just couple those together. And so then you go to the next part. And this is the part. So now I have a raw data. I have a function for pre-processing. And I want to apply the pre-processing function to the raw data. If you remember when we were talking about TensorFlow, see that one of the benefits of TensorFlow is that it creates graphs. So if you do pre-processing over the data, you get basically graphs of operations. So you can pick that graph and apply it later to other data. So basically here what we do, so we're going to basically pass data to this operation, and this operation will gives us three things back. So let's first start with the operation. We are passing the raw training data to TFT BIM, analyze and transform dataset. So this function, this class, analyze and transform dataset, what it does, it gets the raw data, it does the pre-processing over it, it gives you three things back here. It gives you the transform training data after it does the pre-processing over it. It gives you the metadata for that transformation, and it gives you the transformation function as the graph of transformation. So you got the transform data, metadata around this operation, and the graph of transformation. Okay. Now, so this was up to this point was training data. Now, if you want to do the same thing for the test data, the earlier part of the process is they are the same. So basically, you bring the raw test data, you basically do what's called it beam source. You couple these two together, and then you basically pass it to transform dataset function. So there's a difference here. So in the previous one, we say TFT analyze and transform dataset, because we wanted to find the metadata and the graph function. In the test one, you only call to transform dataset. You don't say analyze and transform, because you don't want to build function over the test data. You want to apply what you have from training to the test data. So basically, you call to this. Sorry, you bring the raw test data and the transform function that you created here. You pass that to TFT Beam transform dataset, and that gives you two outputs. One of them is transform test dataset, and the other one doesn't matter. It's like a metadata we don't want. So that's basically what you want. So remember, just the whole idea of like using the training data and applying to the test data. So, okay, so the last part basically is we want to, remember when you got the data, we basically decode the data. Now we want to write the data back, but we want to first encode it and then write it back, because we want to be sure that the format, remember, the TFX-IO wants unified format. So you always, first, if you want to store it, you encode it. If you want to retrieve it, you decode it. It's kind of like to be in that same format. So here, for the training data, first thing is that we need to encode it to be sure that it has a proper format. So we call this function encode training data, beam flat map tuple. We apply a function over, because the data that we have has two things. So we have, where's the data? Transform train data. So transform train data basically has these two, right? It has two parts, a batch and something. We pass the batch to transform data coder and basically encode it. After we encode it, we want to just write it to the hard drive. In the next line, beam IO write to TF records. Okay, and we pass the address where we want this to write, basically. Then you go do the same thing for the test data. You first encode it, and then you write it to the hard drive into some location, basically. And then the last part is you also want that transform function. You want to basically also take that. So you're going to write the transform function to some place, TFTBM write transform function, and wherever is at the address that you want to write it. So you do that and let this run, and basically this create that transform function for you. All right. Let's see, what do we have? Right, I leave the rest of it for you to go through, just how to load it again, because I want to quickly go over TFX. So you have seen TensorFlow transform, you have seen ML metadata, you have seen other TensorFlow labs that we have. And we want to actually look at the TFX itself, that how it simplified all of this process for you. You know, it's kind of. So let's just start with here. So we do some import. So you start by importing the TFX. Then, there is a version of the TFX, you can just run it. But if you want to visualize it, have some like interactive access to it, you can basically say TFX orchestration experimental interactive context. So that means that this context grouping that we create is going to be interactive. So you import that, you load the data. This part doesn't matter, whatever. So then everything starts from here. Because here we're going to have one context only. So you basically create a context called interactive context. Okay. And again, you can just normally use context, but interactive context, it gives you dashboards and stuff like that. That's the whole idea. So you create this interactive context. Now, you remember all the steps that we did before. Load the data, create a statistic, create a schema, data validation, right? So the step one was load the data, and we saw this image before. Example generator, then a statistic generator, a schema generator, example validator, transform. Those are like all the components in order to build the pipeline. So we start with the first one, which is data generator. Basically, you say that TFX dot component CSV example generator, because you're reading it from the CSV. So you basically generated, instantiated this. Now you need to run it. You say context.run that basically that component. So context.run that component. And it basically uses the Apache Beam. It goes, reads, and all the data basically brings it back for you. Now, this is the interactive part. So it gives you this one. It tells you that, well, there's execution result. This is the ID. Remember metadata store, you had execution ID. So that's the execution ID. This execution is a CSV example generator. These are you see, it has a nested fields, everything for you here. What are the properties? These are the properties. Remember, in the previous lab, we manually defined properties, but it's like a TensorFlow has defined those for you. And gives you also example, and also it tells you that where the artifact are stored for the example. For example, say example 21 is stored here at this location on your machine. So now, if you want to access an example, you basically say, you call to this example gen. You say dot output. How do I know? Should I call to output? If you have access to this, where is the data component output? And inside the output, you see these examples, right? So you say outputs, examples, and after that you say get number 0, right? So basically you say give me the first one, and this one, because if you have access to it, it has type, URI, span, split names, and so on. So it finds the data, it says what's the split name and what's the artifact URI. Now, you can basically combine those two and access the file. The file is like a zip, basically compressed file. If you want to load a file, which is compressed also, it's just another version, TensorFlow data. TensorFlow data is a record zip file, compression type, gzip, it basically loads it for you, okay? So now, so there's this basically function that if you basically run it, it takes a bunch of sample, basically it parses examples out and return the records for you. It's just an example for you how to, if you want to manually access the data, that's like a TensorFlow data type, how you can load it. And if you run that, it basically returns the data. So this is the data, that actual data that we have. Now, what we want to do, we want to create a statistic on this and then a schema on this. So TFX, again, make it much easier. So as you will see here, TFX.component statistic gen, and you give the one example to it, and the example comes from example gen output, the examples basically. So that's the data that you can read for the creating the statistics, and you say context.run, and it basically goes through the data and creates that basically statistics for you. Again, it will have similar story, but let's look at here. So it's an execution, and it has input, output. Remember here what we defined manually? Declared input, declared output. So that's basically the same thing. Input, output for that basically event. So execution results. So and then you can access those. Now, if you want to make it visualize it to make it easier rather than manually open this, context.show. And you can say, what do I want to see? I want to see the statistics, this one, the one on the bottom, output statistics, and gives you this dashboard also. Okay, so then we saw this before. The next thing is that we want to create a schema, TFX component, a schema generator. And a schema, what does it need? It needs the statistics first. So a statistic generator output the statistics, you pass it to the schema, and it creates a schema from over the statistics. Context done run a schema generator, basically gives you the same idea. You can again visualize it, and that gives you this part. Now, if you want to do anomaly detection, TFX component example validator. This is the statistic, this is the schema, okay? And context.run, it basically run this and it said like, show me if there's any anomaly. This is where there was no anomaly, for example. And now if you want to do TensorFlow transform, bring the transformation as part of your pipeline for data processing. So what this code does, it just write all of these components to this .py file that you see here. Okay, so if you put this on top of your like a chunk, write files, it will basically write whatever you see in this chunk in the py file. And this is just what this we do some simple data pre-processing. Technically, we just change the name of the features, nothing much. Okay, then we create another transformation. In this transformation, we do more what we do technically. For anything that's numerical, we scale them to 0 to 1. For anything that's categorical, we bucketize them. For anything that's categorical, anything that's bucketing, we bucketize. Anything that's categorical, we basically apply vocabulary to it, compute and apply vocabulary, like if it's a text, for example. And then we basically return all the outputs. So we do three things for numerical, for bucketized data, and for categorical data. This transformation, what it does. Now, what we want to, so we have this, you have this .py files, and you want to bring them, put them in part of your pipeline, TensorFlow pipeline, which if you go up here, is this piece on the bottom. If you have that piece done, then after that, you just need to develop a model, evaluate it, push it to wherever you want. Okay. So if you go down here, so now we have this pre-processing function. So all you need to do is a TFX component transform, because I'm transforming the data. This is the data. This is the schema. This is the module file. Module file means the pre-processing functions that you have, which is the one that we just saw above. And then you say context.run. So this basically takes a while to run because there are lots of data and it just basically try to optimize those. We just wait for that to finish. After that one is finished, then you can get the tensor transform graph, the graph of the transformation. You can get the transform data, metadata, and you can basically access those by basically address also. So in summary, while this one is running, I think what